أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. I welcome you all in today's online session. Hope you all are fine and we start today's session. So our today's session is on the phenomena of corona, electrical power system of transmission, factors affecting corona loss, power loss due to corona, radio interference due to corona. So these are the impacts of topic index related to the today's session that we need to be discussed in uh, session. So the phenomena of corona, we start the slide. So corona is a phenomena whereby the air around the conductor is ionized. Consider a single phase two wired system whose spacing is large as compared to the diameter of the wires. When a low alternating voltage is applied across two conductors, there is no change in the condition. So the phenomena of conductor is the air is ionized around the conductor in specifically in a single phase of conductor and in a large compared to diameter. So it is produced in our transmission line, which is above of starting from 132 kV towards 220 kV and 500 kV onwards. So when a low alternating voltage is applied across two conductors, there is no change in the condition of the air around. If the applied voltage is gradually increased, it will result in a gradual increase of the voltage gradient. So voltage gradient is a potential and overall aspect of the impact of voltage that is produced in the power transmission. The moment it reaches the maximum value, as an example, about 30 kV per centimeter, that is the peak value, or 21.1 kV per centimeter, that is the value RMS. So there is a difference between the peak value and RMS value. The air surrounding the conductor starts conducting with a hissing sound. It is also the vibrating sound. It is also the humming sound. It is also, we can say, hissing and chattering sound, which is uh, like type of sound which is produced and can be heard near the transmission line of tower. In dark, a faint violet glow occurs around the conductor and ozone is produced in physically, which is appear due to the corona impact effect. So and it is effect is called the corona. And uh, up till now, any one of you if have any kind of question, query or difficulty, please feel free to discuss. I will answer the kind of question, but remember the this effect of corona is produced on electrical power system of transmission. This phenomena of corona is not COVID-19. Further, this corona glow around the conductor is uniform throughout the length of the conductors and polished and smooth, and if not, the glow appears only at the rough points. In case of HVDC transmission lines, there is a difference in the appearance of glow on the two conductors. So in HVDC, the corona effect of glow also be appear, but the glow of that corona in AC HVAC transmission line of system is in different of type. The positive conductors will have a uniform glow, and the negative conductor will have a spotty one. So this is the main difference between HVAC transmission line of system and HVDC transmission line of system. So further, the factors affecting corona loss. What are the factors that are effects towards or by the corona loss? The following are the factors affecting corona loss in overhead transmission lines, and it's a impact of overhead transmission line. The concept of corona is not produced in underground transmission line. It's a rule of thumb. Electrical factors as well as impact on the corona losses, atmospheric impact also, and in last factors connected with the conductors. There is a power loss due to the formation of corona that affects the transmission efficiency of the lines. Its effect on regulation, however, is less. This power loss is affected by the atmospheric and line conductors too. So the impact is very much less, the loss is very much less, but as per the analysis of the power transmission and count the kind of loss, we need to analyze and understand the value of the loss. So that's the reason we need to calculate impact of corona loss. Power loss due to corona under fair weather condition is given by, this is the dry formula which we need to study, that particular power that is lost in fair weather is 244, the constant factor, divided by the lambda, multiplied by the f plus 25, the operating frequency on which it works, and delta is the angle of the density of the air, most probably it would be, and multiply by the square root of r divided by d. So r is the radius and d is the separation of distance between the conductors. These voltages in multiplied are we called the phase voltages, and d naught is the nominal kind of voltages with the negative of sign, and whole over the multiplying factor in square multiplied by 20 10 to power minus 5 kilowatt per kilometer per phase peaks formula. So this is the lost impact in power that we need to analyze in kilowatt per kilometer per phase in equation 6.5. So further, the values of impact we called V phase are voltage to neutral in kV, V D naught disruptive critical, voltage to neutral in kV, F is the supplied frequency in hertz. Under abnormal weather condition, V do not is 0.8 times its value. Under fair weather conditions and power loss due to corona is given by the impact in normalized way in this form. So we already aware by the factor, but the changes in formula is 0.8 times D naught. So by in the previous, as per the declared that previous formula, 6.6 formula value would be same. When power loss due to corona is low and the ratio we face by VD naught is less than 1.8, Peterson's formula that Peterson's calculate the particular value is used to determine corona loss, and is given by P equal to 21 into 10 to the power minus 6. This is the factor, multiply by the frequency, and then multiply by the phase voltage in the square, divided by log base 10, separation of distance between the conductors, divided by the radius of conductor, all over the value in square. So multiply the factor, that is the K, and also measure the value of power in kilowatt per kilometer per phase, where the factor K we called, which varies with the ratio of V phase by VD naught. So this is the nominal factor that we represent in our previous session. So this is the descriptive normalized formula as well, with the normalization of simplifying ratio factor, that is the value of K, and derived by Peterson's formula we called in 6.7 equation. So further we need to calculate the power loss in corona effect. A three-phase 220 kV 50 Hz transmission line has equilateral triangular spacing. Equilateral means the separation of distance between the three conductors is same with A to B, B to C, and C to A. Again, this equilateral triangle have the same spacing between the conductors. Line has equilateral triangular spacing of side 2 meters. The conductor diameter is 3 centimeter. The air density factor and irregularity factor is 0.95 and 0.83 respectively. Find a disruptive critical voltage and corona loss per kilometer. Assume any data required. So coming toward the solution and data, line voltage is 220 kV. This particular voltage is line to line voltage. Operating frequency is 50 Hz. Spacing between the conductor, that is the D, equal to 2 meters, and equilateral spacing means every conductor spacing with another is same, that is the 2 meter. Radius of conductor R equal to D by 2, that is 3 of diameter divided by the 2, we got the value of radius, that is 1.5 centimeter. The irregularity factor M not we called, that is 0.83. This is the irregularity factor. So I was sure about the density, that is the sigma. Sigma value is air density, that is 0.95, which is mentioned. So these are the irregularity factor and sigma value of density respectively. So 0.95 is the air density and 0.83 is the irregularity factor. Further, the assumed dielectric strength of air G naught is 21.2 kV per centimeter. So we assume the dielectric strength of air. Dielectric means the spacing effect and the you can say the separation effect between the conductors, 1 by 2 and 2 by 3 and 3 by 1. The medium in between the conductors we assume and we know it is air. So the dielectric strength of air we need to be considered in the factor G naught, that would be 21.2 kilo kV per centimeter. So further moving towards the formula, the disruptive critical voltage VD equal to M naught G naught sigma into R ln d by R. So this is the kV voltage. So M naught is 21.2 into 0.83 G naught, and as sigma into R, that is the 0.98, and that sigma is the air density, multiply by the 0.5 times the value of R is the radius of conductor 1.5, and then ln into separation of distance 200 and the radius is 1.5. So by the calculating of all these values, we got 100. Simplification after that, we got 122.685 kV. So this is the destructive critical voltage, which is we found by the formula VD. Corona loss, we coming towards the corona loss, actually a power loss by the corona effect. We need to find by the factor 244 is a constant factor, normalizing effect of factor constant, multiply by the effect F plus 25 divided by sigma. So F is the operating frequency of the transmission line, 25 is the again factor, divided by the sigma, that is the air density, multiply by the square root of d divided by r divided by d. R is the radius of conductor and d is the separation of distance between the spacing of conductors. Then V minus Vd naught. So these are the line voltages 220 kV, and the destructive critical voltage Vd we found is 122.685 kV. So this is the disruptive and disturbance and affecting critical voltages, which is form and disturbance form of voltages, deformation of voltages due to these kind of effects, that is 122.685 in kV. factor would be in a square multiplied by 10 to the power minus 5 kilowatt per kilometer per phase in measurement. Further, we put all the given values in the data in the formula, and we got the simplification form. And after simplification and solving, we got the value of corona loss and power is 0.3106 kilowatt per kilometer per phase. So this is the corona loss per phase per kilometer and per kilowatt value. The power has been loss that would be in watt, you can say, per kilometer per phase would be 310.6. So this is the particular power which most of the time we ignore, and it can be reduced in different kind of aspects. So moving towards the total corona loss, that is 3 into 10 to power 0.3106. Why multiply by 3? Because the system is in three phase, and the corona effect gradually, totally, and by average aspect, we need to be calculate by multiply by the aspect of 3. So the value of the result by multiply value 3, we got overall three phase system of electrical power transmission. The corona loss would be 0.9318 kilowatt per kilometer. Now it's not per phase, now it's we called a three phase. So that's the reason it specifically is not mentioned per phase. So because it is a system of three phase, now we can say that this is the effect of 931.8, and the value of watt per kilometer. This is the power which is waste loss due to corona effect. So this is the impact of corona effect. So further, the following factors of corona loss in overhead transmission line, and obviously in underground electrical power transmission system, there is a no concept of corona loss. So number one is electrical factors, atmospheric factors, factors connected with the conductors. Further, factors affecting the corona loss is electrical factors, effect of frequency from equation 6.5 to equation 6.7. These are the uh, corona loss equation in 6.5, and this one is the corona loss equation, the normalized Peterson formula in Allen model specification. So the corona loss is observed to be a function of frequency loss, you can say. Therefore, increase with the increase of frequency, since there is no frequency in DC. So that's the main point. If the frequency would be increased or frequency would be dealing in AC transmission and system, so there is the availability of corona effect or corona loss, we can say. And specifically similarly vice versa, we can say in DC power transmission system there is a no concept of frequency, so there is a no concept of corona loss, or you can say the less value of corona effect impact in our electrical power system of AC transmission line as compared to DC transmission line. So there is a no concept of frequency in DC transmission line. So the corona loss is less as compared to AC transmission line. So this is the advantages of DC transmission line, you can say, as compared to the AC transmission line. So preferably now world is moving toward the DC transmission line due to the less number of losses. Frequency, we can say, frequently we can say, the effect of frequency, sorry, the effect of DC transmission line or corona loss would be minimum, but as per the count, you can say, as per the count, as per the consideration, as per the comparison of power losses and many kind of effects. So in DC transmission system, the effect of corona would be less, you can say. So further, we can say that the line voltage, transmission line operating voltage largely affects corona loss. So line voltage transmission largely impact in our corona loss. So we need to consider, we need to specify, we need to minimize the corona loss. So these are the some kind of possibility by which the corona can be reduced. So line voltage, transmission line operating voltage largely affect corona loss. Corona loss increase with increased operating voltage. When it exceeds the disruptive critical voltage, affect the load current, temperature of the conductor increase with increase the load current. Therefore, it prevents deposition of snow on the surface of the conductor. This reduces the corona loss. Even also, the heating of the conductor has no effect on corona loss during rain. Number two effect is the atmospheric factor. Pressure and temperature affects corona loss is a function of the air density factor, that is the sigma, and is inversely proportional to the sigma. The corona loss has depends upon the critical destructive voltage. So loss is directly proportional to the difference of voltages of line voltage, that is the V, minus the disruptive VD naught voltage of the square. So if the effect of difference of the square of the voltage can be increased, so the loss would be increased. Even also from the above equation, we see that the critical destructive voltage VD naught depends upon the air density factor, that is the sigma. Therefore, the corona loss increase with decreased value of sigma. For low value of sigma, that is the air density, the pressure should be low and the temperature high. Therefore, the corona loss is more is on hilly areas, you can say, than the plain areas. Dust, rain, snow, hail affect the critical disruptive voltage decreases due to dust particles deposit on the conductor, and bad atmospheric conditions such as rain, snow, and hailstorm. This cause increased corona loss. So you can say these are the critical impact can reduce the corona effect, because in dust or free or other kind of impact in hilly areas, you can say the corona effect would be less, but in plain areas it would be high. And corona can be very much high due to the kind of factors which are atmospheric, rain, snow, and hailstone, because dust is imposed on the suspension insulator of the conductor edges connection, which is going through by the suspension insulator through the conductor connecting to the next suspension insulator of connection. Factors connect with the conductor. So conductor size consider expression given below. So power loss is directly proportional to the square root of radius of the conductor divided by separation distance of the conductor. That particular ratio of distance is the square root is directly proportional to the power loss, and power loss is directly proportional to the difference of phase voltage minus the disruptive voltage of the square is directly proportional to the power loss as given. Also, these are next of equation 6.8 and 6.9, which can also be factor affecting equations represented by the corona losses. We can conclude that the power loss are directly proportional to the square root of the radius of the conductor. In addition, equation 6.9, we can conclude that losses will be reduced due to increased diameter. So if we increase the diameter of conductor, so corona loss would be reduced, because as equation 6.3 in previous, the difference of disruptive voltage effect of voltage uh, by the different kind of aspects proportional to the radius of the conductor. The change of loss due to equation 6.9 is high when compared to equation 6.8. Therefore, the corona losses decreases with an increase in the diameter of the conductor. So spacing between the conductor, from the loss formula, it is seen that the loss is inversely proportional to the square root of the distance between the conductor. So therefore, higher the spacing of conductor separation distance between the conductors, lower will be the loss, you can say. There may not be any corona effect. So if the spacing is made very large compared to their diameters, so corona loss would be reduced, but this solution would be highly costly. So radio interface would be considered in next aspect, next session. So this is all about today's session. Up till now, any one of you, if have any kind of question, query, or difficulty, we can discuss. And all the things if have been clear in your mind, so we end today's session. Allah Hafiz.